Okay, so in these few videos right here, we're looking at different applications involving linear and quadratic equations and kind of seeing how to set them up and solve them. I said in the last video I was just going to use some problems from your book so you could follow along. And now we're actually going to go over page 90, number 10. And this is what's called a mixture problem. We have names for everything in math to kind of group stuff together. The goal here is to actually see the similarities between this problem, the next problem we'll do, and actually the last problem. There's a reason we do all these at the same time, because they're all very similar. So if you look at problem 10 on page 90, it says a nurse mixes 60 cc's of a 50% saline solution with a 10% saline solution to produce a 25% saline solution. How much of the 10% solution should he use? And in this case, well, first off, I will say, if you are unclear what that means, a 25% solution means if you have, say, 100 ounces, 25% of that solution is saline. So there's 25 ounces of saline. If it's a 20% solution, there's 20 ounces of saline. So we kind of get the idea of what that means. Now we just want to set up how to actually solve it. We said the first thing we do is look for our variables. And in this case, how much of the 10% solution should he use? We're only looking for one quantity. Last time we had two quantities, so we needed two different ways to write them. Here we're only looking for one quantity, so we'll just call it x. X equals the amount of the 10% solution. And now that I have my variable, I should be able to generate an equation. And that doesn't seem like much to go on, but we can actually use the same idea we did with our interest problem. Let's see. A nurse mixes 60 cc's of a 50% saline solution with a 10% saline solution to produce a 25% saline solution. So while we're talking about saline solutions, the idea is the same as the interest problem we did before. If you remember on the last video, we had interest from the first account plus interest from the second account equals total interest. Well, here I can do saline from the first solution plus saline from the second solution equals total saline. So let's see. A nurse mixes 60 cc's of a 50% saline solution. So 60 cc's, and it's 50% saline. With a 10% saline solution. So let's see, my 10% solution, that's the one I want. So I guess it's x cc's times 10% 0.1. And then I'm told I want a 25% saline solution. So that's 0.25. And the only question is, well, what goes there and kind of how do I relate these? But again, if we do what I use for interest, this is the saline from the first solution. This is the saline from the second solution. If I add them together, they should equal the saline from the total solution. So that makes sense. The only question is what goes here. This is different than the one we did last time, which is kind of why I'm going through it, so you can see the different ways to set up and solve these problems. I don't know how much of the total solution I have, but if you think about it, I mixed 60 cc's here with x cc's there. So how much did I end up with total? 60 plus x. If you recall before from the interest problem, I had the total and I subtracted to get my quantities. Here I'm not given the total, so I add the amount of my quantities to get the total. Now I have an equation and I can do the algebra and solve it. Let's see. 0.5 times 60, that's 50% of 60, which is 30, plus 0.1x equals 0.25 times 60, a quarter of 60 is 15, plus 0.25x. And now solve that. And in this case, since 0.25 is bigger than 0.10, I'm going to bring this x over. 0.25x minus 0.1x is 0.15x. Subtract the 15 over. 30 minus 15 is 15. And I get 15 equals 0.15x. And really quickly, that means 15 equals 15 over 100x. Divide the 15 and multiply the 100 over. You get 15 times 100 over 15 equals x. The 15's cancel, and I get x equals 100. You guys don't have to do the algebra this way. When you're solving it out, you can just divide the 0.15 there and be done. I just didn't feel like grabbing my calculator. But essentially, that means I have 60 cc's of the 50% solution, 100 cc's of the 10% solution, and that gives me a 25% solution that's 160 cc's. Again, I'm not going to check this, but you guys, if you're so inclined, can plug those numbers in and make sure they work. I know they will, so I'm not going to take the time here. The last problem we want to go over. In your book, it is number 14 on page 90. And let's see, it says, a plane travels 800 miles from Dallas, Texas to Atlanta, Georgia, with a prevailing west wind of 40 miles per hour. The return trip against the wind takes a half an hour longer. Find the average speed of the plane in still air. So again, much like with the mixture problems, you have to have an understanding of what's going on. For the purposes of this, essentially the idea is, I'm not very good at drawing planes, so I'm actually going to draw a boat in a river because the principle is the same. I'm also not very good at drawing boats. But for the sake of argument, suppose this is a river. Oh, I have a blue marker. Suppose this is a river, and there's my water right there. And there's a current. And the current is, say, 10 miles per hour that way. Now suppose I'm in my boat. That's the best boat I can draw. My planes look worse, which is why I'm using this. And we understand how this works. Suppose my boat goes this way at 20 miles per hour. How fast does it go? Well, my regular speed without the current is 20 miles per hour. But if I go this way against the current actually slows me down. And in this direction, I only go 10 miles per hour. But if I then turn around and come back, when I go in this direction with the current, my speed is actually 20 miles per hour plus 10, 30 miles per hour. That's essentially what we're doing here with planes. We're looking for my average speed, my speed without the wind or without the current, understanding that the current is changing my speed. So now we can kind of set the problem up. Let's see. A plane travels 800 miles from Dallas to Atlanta with a prevailing west wind of 40 miles per hour. The return trip against the wind takes a half an hour longer. Find the average speed of the plane in still air. Again, much like the last problem, I'm only looking for one quantity. So we'll just say x equals my average speed without the wind. And now this setup can be a little bit different, but let's see, if we kind of figure out all the information I have, a plane travels 800 miles, I guess that's my distance, and let's see, the west wind is 40 miles per hour, so a 40 mile per hour wind. And the return trip takes a half an hour longer. So going home takes a half an hour longer. And I have to find a way to relate all this information. And in this case, like I've said before in the last few problems, there's different ways to set these up and solve them. So here I'll actually use a different setup. Once you understand what you're doing, you can set these up much quicker. I'm just showing you different ways to set them up so you can use them if you get confused. And in this case, I'm going to use a table just to get an idea of what's going on. Let's see. I have my trip, we'll say there, and then back home. And, well, let's see, if I'm talking about distances and rates and times, we can use the distance formula that we mentioned last time, d equals RT. And let's see, well, for my rate, Well, when I go there, let's see, since going home takes me longer, it means when I go there, I'm going with the wind. So what's my actual speed, my rate going there? It's my average speed that I'm looking for, but then the wind speeds me up by 40 miles per hour. When I go home, what's my speed? Well, it's my average speed without the wind, but then the wind slows me down. I wrote 50, and it's obviously a 40. Well, okay, let's see. What's my distance? My distance is 800 miles there, and clearly it's the same trip, so it's 800 miles back. What's my time? Well, all I know is that one trip takes a half an hour longer, but in this case, we have this formula, we can use it. Earlier in the semester, we talked about solving equations for one of the variables. Solve this variable for t. T equals d over r. So in this case, t is equal to d, 800, over r, x plus 40. Here, t is equal to distance, 800, over x minus 40. And now I have my times. And I'm going to have to erase a little bit of this just because of the size of this whiteboard. But now, I need a way to relate those quantities, and I'm told in your book and in the part I just erased, my return trip takes a half an hour longer, which means the trip there, that time, which is 800x plus 40, if I add 1/2 to it, I'll get the amount of time it took me to get home, which is 800 over x minus 40. And now I have an equation. The time there plus a half an hour equals the time coming home. Now I just need to solve that out. And in this case, well, let's see. We know how this works. I'm going to have to multiply by the LCM to clear the fractions. And in this case, I have 3 fractions. So my LCM is going to be 2, x plus 40, x minus 40. Multiply everything by that. And since this video is getting rather long, I'm going to kind of go through this quickly. The first term, the x plus 40s will cancel. So you'll get 2 times x minus 40 times 800. Plus, for the second one, the 2's will cancel. And you'll get x plus 40, x minus 40. Equals, for the last one, the x minus 40s will cancel. You'll get 2 times 800 times x plus 40. And then you'll just have to solve all of this out. So you'll get 2 times 800, 1600 times x minus 40, plus, here that's a difference of squares, x squared minus 40 times 40 is 1600, equals 800 times 2 is 1600, times x plus 40. And now from there, that's a quadratic equation. So we understand how we're going to solve this. Distribute the 1600, distribute the 1600. Since it's quadratic, bring everything to one side, set it to 0, and solve it. Either factor it or use the quadratic formula. And because this video is rather long, and because this is a problem I'm going to give you for homework, I gave you all the setup and gave you most of the algebra. You guys get to do the rest. At this point, you guys know how to distribute, you know how to solve quadratics, you know how to set to 0, you get the quadratic formula, you know how to check your work, which means you should be able to work through all of this on your own. The last thing I'll stress, keep in mind when solving these, like I've said before, all the algebra we know works itself into each problem. We had to use a distance formula, create this table, get an equation, which was a rational equation, so then I multiplied by the LCM. Doing that gave me a quadratic, which you guys are going to have to set to 0 and then solve. So understand that all the algebra you do is always fair game on every problem.